Segmentation and paging. Have you ever wondered how your computer runs Chrome, Spotify, and other apps at the same time without them crashing into each other? That's what we are going to learn today. By the end of this video, you will know exactly how your computer keeps all of that memory safe and organized. So let's let's start with the big question. Why does a computer even need to manage memory in the first place? We are going to cover all of these things in our presentation today. We will look at why memory management matters. Then we will cover segmentation step by step. And then after that we will do the same thing for paging. And we will took all 5 types of paging used in the real system. We will look all we will look at 5 types of paging used at modern systems. Then we will compare segmentation with paging side by side, and we will finish with how modern computer uses both ideas together. Alright, alright, let's jump into the first one. Our slide number 3. Here is our slide number 3. Why memory management? Every program that runs on your computer needs space in RAM. It needs room to store its instruction and its data. But RAM is limited, and your computer isn't running just one program, it is running multiple programs at a time. So someone has to manage all of that space. That's the job of operating system's memory manager. It does three main things. It gives each program the memory it needs, it protects one program from touching another program's memory, and it tries to use all the available RAM as well as it can. Now, there are two classical ways to do this job. The first one is called segmentation, and we are going to talk about this first ones. Now go to slide number 4. What is segmentation? Segmentation breaks a program into logical parts, not into equal pieces. Think about any program. It has code, which is the actual instruction. It has data, like global variables. It has a heap for memory, the program state while running, and it has a stack for function called and local variables. These four parts are different from each other. They grow at different speeds, so segmentation gives each one its own space and lets that space be any size it needs. This is why segmentation feels natural. It matches how programmers already think about their code. Now let's see how the computer actually finds these segments in memory. Let's go to slide number 5. How segmentation works. Every address here has two parts, a segment number and an offset. The operating system keeps a segment table for each program. This table has one row for every segment. Each row stores two things, the base address, which is where the segment starts, and the limit, which is how big it is. Here is how translation works. First, the computer looks up to the segment in the table. Then it checks, is the offset smaller than the limit? If yes, it adds the offset to the base address, and that keeps the real address in RAM. But if the offset is too big, the hardware stops right there. It raises what's called a trap. That's the protection step doing its job. Let's see this with the real number next. Slide number 6. Example for segmentation. Let's say our code segment started at address 5000 and its size is 2000 bytes. First case, a valid access. Our address is code offset 300. 300 is smaller than 2000, so this is allowed. We add 5000 plus 300 and we get 5300. That's the real address in RAM. Second case, an invalid access. Same segment, but the offset is 2500. That number is bigger than the limit of 2000, so the hardware doesn't even try to math. It raises a trap right away. This is what people call a segmentation fault. That trap is the whole point of segmentation protection. Now, segmentation isn't perfect. Let's talk about its pros and cons. Slide number 7, Advantages and Disadvantages of Segmentation. Slide number 7, Advantages and Disadvantages of the segmentation. Let's start with the good parts. Segmentation matches how programmers think. It makes protection simple since code can be locked as real only. It supports sharing so two programs can use the same library agent and work well for modular programs. Now the downside, because segments come in different sizes, free memory end up broken into small scattered pieces. This is called external fragmentation. Sometimes the operating system has to stop and clean this up, which takes extra time. That fragmentation problem is exactly what our next idea, paging, is developed. It solves the problem of fragmentation. Now let's go to slide number 8. What is paging? Paging takes mm, Slide number 8. What is paging? Paging takes a totally different approach. Instead of following the program logical parts, it cuts memory into equal size pieces called pages, and it cuts RAM into pieces of the exact same size called frames. Because every page and every frame is the same size, any page can go into any free frame anywhere in RAM. There is no need for one big connected block of space. This simple idea is why almost every modern computer uses paging. Windows, macOS, Linux, Android, all of them uses paging. Let's see how the computer finds the right page. Slide number 9. How paging works. Just like before, the address has two parts, but this time it's a page number and an offset. Instead of segment table, we now have a page table. It maps each page number to the frame that sold it right now. To translate the address, the computer looks up the page number, finds the frame, and combines the frame base address with the offset. That gives us the real physical address. Because pages and frames are always the same size, the offset can never go past the page size. So there is no risky bound checks and no external fragmentation at all. Let's run through a full example. Slide number 10. Paging example. Say our page size is 4 kilobytes. In numbers, that's a 4096 byte. Our address is 9500. Step 1. Find the page number. Divide 9500 by 4096 and round down. That gives us page 2. Step 2. Find the offset. Take 9500, subtract 8192, that leaves with 1308. Step 3. Check the page table. It tells us page 2 is sitting in the frame 7. Now we combine everything. 7 times 4096 is 28672. Add our offset of 1308 and we land on 29980. That's our real physical address. The program never sees any of this happening. It just thinks it uses address 9500. The translation happens quietly every single time. Now let's look at how real system uses paging in practice. Slide 11. Types of paging. Real computers rarely use the simplest form of paging. Here are 5 common types. Number 1. Simple paging. Loads every page right away. It's easy but it can waste a memory. Number 2. Demand paging. Loads a page only when it's actually used. This makes program start faster. Number 3. Multi-level paging. Split the page table into smaller levels. This helps with the very large programs. Number 4. Hash paging uses a hash function to find pages quickly. This works well for huge address spaces. And the last one, number 5, an inverted page table keeps one entry per frame, not per page. This keeps the table small even for big programs. Most modern systems combine demand paging with multi-level tables. Now let's compare segmentation and paging directly. Slide number 12. Segmentation versus paging. Segmentation uses a block of different sizes. It follows the program's logical structure, but it can suffer from external fragmentation. Paging uses blocks of the same size. It follows the physical layout of RAM. It may waste a little space inside the last page, but it never has external fragmentation. So it really comes down to this: logical structure or physical efficiency. In the real world, computers usually use both. Let's see how. Let's go to slide number 13. Real world use combining both ideas. Most operating systems don't pick just one method. They usually use paging as the main system, but they still borrow ideas from segmentation. They usually, for example, older x86 system divided memory into segments and then paged each segment. This combined the best of both ideas. Paging is also a reason virtual memory works. Every program gets to believe it has its own large space, even if some of it is stored on the hard drive. And there is one more helpful piece of hardware, the TLB. This is a small, fast memory that stores recent page lookups so the computer doesn't have to search the full page table every single time. Alright, let's bring everything together. Slide number 14, Summary. Let's review what we learned today. Paging organizes memory into equal sized blocks. This avoids external fragmentation completely. In real system, paging usually does the heavy lifting, while segmentation idea still show up at the higher level. Together, these two ideas are why your computer can run many programs at once safely using the same RAM. Okay, this is it for today's presentation. If you have any questions, feel free to ask